and welcome back to this series explaining the science behind solar panels, batteries, inverters and green energy. So today I'm going to be talking and explaining to you how a solar panel works. So what's happening on the roof in those panels to actually generate electricity. This episode is going to have to go into a bit of the in-depth science of semiconductor physics, so you'll have to bear with me on that, but I'll try and explain it in basic terms that everyone should be able to understand. Also, I'm not going to talk about the problems of solar panels. That's going to be in a different episode, and that will also look at how the technology of solar panels is developing and where it's going and where it's been and how those problems have been overcome. So now let's look back at how a solar panel actually works. And I'm going to take the example of a silicon solar panel because those are the most common ones and the ones that happen to be on most people's roofs. Silicon is one of the most abundant materials on planet Earth, and it's easily obtainable in the form of sand, which then gets processed and turned into pure silicon. And this forms the base of our solar panels. So let's go back to some GCSE level chemistry. Silicon has 4 electrons in its outer shell, but GCSE chemistry tells us that atoms like to have 8 in its outer shell because this fills its outer shell up. So the way that silicon does this is by sharing electrons. So one single silicon atom is then bonded onto 4 other silicon atoms as shown here, and this then gives it 8 electrons in its outer shell, and this is covalently bonded. Now, in semiconductor physics we have a process called doping, and this is a way of improving the conductivity of a semiconductor. And the way it's done is by adding an impurity into the silicon lattice, and you can get something called N-type doping or negative doping and P-type doping or positive doping. And in order for a solar panel to work you need both of these. So what happens is you take your pure silicon and you implant it with phosphorus if you want a N-type semiconductor or N-type silicon. So you bombard or you incorporate phosphorus into the melt when you're forming it, or you bombard it and do ion implantation. And what happens is that one of the silicon atoms gets replaced by the phosphorus atom. And what this does is that phosphorus has 5 electrons in its outer shell, which means that 4 bond into the lattice and you have this 1 extra electron hanging around, which can be used to conduct electricity. So you improve the conduction in that way. So this is why it's called N-type doping or negative doping, because you introduce that negative electron into the lattice. The other way of doping, or P-type doping in silicon, is done via something called boron, which has 3 electrons in its outer shell, which is also sometimes known as the valence shell. And in this case, what happens is that you get your lattice and then you have a boron atom incorporated in, which bonds with 3 silicon electrons, leaving what's known as a hole, which isn't quite the opposite of an electron. It's not a positron, which is an antimatter electron, which has a positive charge, but it effectively acts as a positive charge. And what electrons can do is hop into this hole, and then the hole progresses from one side to another under an electric field. So it can be seen as a carrier, or an electricity carrier. So that's how it increases the electrical conductivity of the semiconductor. So in a solar cell, what you do is you make a sandwich called a PN junction, and this is the same technology or same science that creates LED lights as well as diodes. So diodes prevent electricity flowing in one direction, so they're in a lot of devices. Now you have a sandwich where you have a piece of silicon which is N-typed sandwiched up to a piece of silicon which is P-type. And what happens at that interface is that the electrons in the N-type will move and also towards the P-type semiconductor, and the holes in the P-type will move towards the N-type because they're trying to neutralize each other. And what happens is you get something called a depletion region where these electrons and holes form electron-hole pairs. So you end up with an area of what's called depleted, which is depleted of charge. So it's very difficult for electricity to pass across this interface. And this is the real key part of how a solar panel works, because what happens is that at the N-type interface, because you've taken electrons away from it to form this depletion region, you end up with a positive region. And on the P-type side, you end up with the opposite out. Because the holes have moved away, you end up with sort of excess electrons there, which means you get negative. And when you have a positive and negative layer, you end up with an electric field between the two, which means that any electrons within that electric field will move. Unfortunately, what's happened is that those electrons are bonded to holes, so they're effectively neutral and they can't move. Or you can look at it this way, that the electrons are trying to be drawn towards the positive part of this N-type interface, and the holes are trying to be drawn towards the negative part, which is now the P layer, or P-type semiconductor. So they're fighting against each other, so they're not going to move. However, when light hits this depletion region, it gives enough energy, it transfers the energy, as light is an electromagnetic wave, which is a transfer of energy, to this electron-hole pair, and it causes them to split apart, in which case the electrons then flow towards the positive in the N-type, the holes flow towards the negative, which is in the P-type, so you get this flow of current, and that is electricity. So if you then connect your N-type N-type side and your P-type side with a wire with some sort of load in between, say a house, or an inverter, which is using that electricity, you get the electrons flow in and the holes flow in, and you get a current. So that's how the solar panel basically works. So in principle, what you have to do is get the light to go into the depleted region. And in order to do that, you create your N-type region very, very thin, so light can penetrate through and go into the solar panel. You then put metal on the back of your P-type, which acts as the contact around, and you put little metal strips along the along the inside part of your solar panel to take the current away that way. Or you can put down a transparent conducting layer, such as indium tin oxide. So that's how a solar panel worked. So I'll do future episodes looking at the problems of solar panels and how they've been overcome, and also where the technology will be going in the future with things like perovskite solar cells. So hopefully you found that useful and explains a little bit more about what's happening on your roof when you're generating electricity.